Imagine this. Everything you've ever known, the stars, galaxies, and even your own body, is nothing more than a projection from a distant cosmic boundary. This is not a plot from science fiction, but a real theory emerging from the frontiers of modern physics. Welcome to the mind-bending world of the holographic principle. The idea sounds almost absurd at first. How could our rich, three-dimensional universe actually be encoded on a two-dimensional surface? To answer this, we need to dive into the nature of black holes. Back in the 1970s, physicists like Jacob Bekenstein and Stephen Hawking discovered something strange. The amount of information you can store in a black hole is proportional to the area of its surface, not its volume. This contradicted what we thought about ordinary matter, where information scales with volume. It was as if the entire content of a black hole could be described by data on its event horizon, the outer shell. This gave rise to the shocking idea that information in the universe might be stored on boundaries, not within the space itself. In the 1990s, physicist Juan Maldacena provided the most concrete realization of this with what's known as the ADS-CFT correspondence. This theory proposed that a type of quantum field theory, called conformal field theory, or CFT, in a flat space could be exactly equivalent to a gravitational theory in a curved higher-dimensional space called anti-de Sitter space, ADS. In other words, a universe with gravity in a higher-dimensional bulk could be fully described by quantum physics on its lower-dimensional boundary, with no gravity at all. This was the first compelling mathematical demonstration of a holographic universe. Now, there's a catch. Our universe is not an anti-de Sitter space. We live in a universe with a positive cosmological constant, one that's expanding and dominated by dark energy. But many physicists believe that the holographic principle may apply more generally, beyond ADS spaces. If this is true, it means that our own four-dimensional universe, including everything we see, feel, and experience, could in principle be described entirely by information on a distant, two-dimensional boundary. To be clear, this doesn't mean we live in a computer simulation, though it's easy to draw parallels. Instead, it's more like the universe itself has an informational foundation, and the 3D world we perceive is a kind of projection or emergent phenomenon from deeper quantum laws. It challenges our most basic assumptions about space and reality. Think of a hologram on your credit card. It looks 3D, but all the information needed to create that illusion exists on a flat surface. The holographic principle suggests something similar might be true for our entire universe. But what does this mean for physics? If gravity in our universe is an emergent property of quantum fields on a boundary, it may open new doors to unifying general relativity with quantum mechanics. It also reframes how we think about space and time, not as fundamental ingredients, but as derived from something more basic: information. The holographic principle aligns with growing ideas in physics that information is more fundamental than matter. This can be seen in black hole entropy, quantum entanglement, and even recent studies into quantum error correction, where the structure of space-time seems to arise from patterns in information networks. In this view, our universe is a quantum code, and we are subroutines in a vast informational system. Of course, this is still highly theoretical. We don't yet know how to apply holographic dualities to our real expanding universe. But researchers are making progress. New ideas in de Sitter holography, entanglement entropy, and even emergent space-time are pointing toward a deeper theory, one where space itself is not a container for matter, but a construct built from relationships between bits of information. Imagine a universe where geometry and gravity arise from entanglement patterns, like a spider web of connections stitching the cosmos together. The implications are staggering. If this theory holds, it means that every point in space, every moment in time, every particle and planet, all are part of a vast tapestry woven from information. We are not just observing the universe. We are the universe, processing itself through quantum entanglement and holographic encoding. And if reality is built on information, it may also be programmable, not in the sci-fi sense of hacking the matrix, but in the sense of understanding and manipulating the deeper rules that govern everything. We stand at the edge of profound discoveries. The holographic principle may not just explain gravity or black holes, it could rewrite the story of existence itself. So the next time you gaze at the stars, ask yourself, are you looking into the universe or looking at the surface of something deeper?